Good afternoon. All right. Thank you. Okay, good. And you can, okay, sorry. And okay. Can I, before I say that, I'm gonna have to add a new part to this routine. Well, first of all, sorry I'm late. I am a little bit late here for no good reason, but can I do a thing where, can one of you use your voice to tell me whether you're hearing my voice right now? Can we add?
Yeah, we can hear you.
I can hear you.
All right, awesome. And let's even, I love I'm going to do the good afternoon things now. I love that you all do that. But maybe like as part of the deal for me, like if we can always, if someone can do a vocal good afternoon in the future, like that might break the, anyway, you get my point. All right, cool. Thank you. So here we go. And I am sorry I'm late. That's totally my bad and no good reason for it. So good afternoon, Daniel. Excuse me. Good afternoon, Luna. Good afternoon, Sam. Good afternoon, Nikaya. Good afternoon, Yorgelis. Good afternoon, Camilla. Good afternoon, Darina. Good afternoon, Alyssa. Good afternoon, Jenna. Sorry. Good afternoon, Ashley. Well, it's all good afternoon. This is like strange new consistency. Okay, it's great to see. Good afternoon. Whoa, Jerry's iPhone, which is, wait, who? I think I know who that is. Wait, Jerry's iPhone. Wait, I know, I can, wait, who is Jerry's iPhone? Jerry, wait. Can I figure this out without Jerry? Who's Jerry? All right, I'll figure it out as we're going. But good afternoon, or you'll tell me. Okay, no, I give up. Oh, and sorry. Good afternoon, Amarani, and good afternoon, Ashley, and good afternoon, Jenna. Did I totally miss? Oh, wait. Okay, I lost it. Anyway, okay, it's been too long. Good to see you. Maybe Jerry's iPhone will tell me who Jerry's iPhone is, or maybe not. Okay, it is good to see you. We are going to start. It's been a long time. I hope you've had some sort of something. Well, I know you've had some craziness with weather. Anyway, hang on. Okay, we have some catching up to do. Let me do a couple of the logistical items since it's been a while. Okay, number one, more people are coming. Hold on. Okay. Well, actually, this is important. Actually, I'm gonna put this in the chat. Hold on.
Professor, I had a quick question.
Yes, 1 second. Let me just type it. Yes, one quick second. Okay, one quick thing before we get Ashley's question, just to tell everybody, and I just put in the chat to be clear, we do have to end a little bit early today. It's a little bit unusual. Just for reasons on my side, we have to end a little bit early. I'd like to end 15 minutes early. If I'm on some major roll or something, like I could maybe go to 10 minutes early, but I'd like to try to leave 15 minutes early, and I'll make it up to you in some way. I mean, I'll make up the instruction time to you somehow. Excuse me, but feel free. If there's like when there's 20 minutes left in class, when it's like 1:10, please feel free, especially if I seem to have lost all sense of stuff. You could put in the chat, or you can even chat out like, there's only 20 minutes left, professor. And like, I won't be. Oh, okay. Got you. Okay. So that's one thing, is that we're ending early, and please feel free to let me know if I start, give me a 5-minute warning before that happens. Then second of all, Ashley, go.
Okay, hello. So I just wanted to know that for the for homework 3, is it still due on Tuesday? Because I know that we didn't finish going over homework 1 yet, and I'm not sure if we're gonna go over homework 2, just because it is like a review of like all math that we should know. But is it still due Tuesday, or like, is it okay if we hand it in a little bit later because we're still going over like homework 1 and everything?
Yeah, no, that's a really good question. That's a totally fair question. So first of all, it's totally okay if you hand in a little bit later, number one, anyway, like even if I don't change the date on it, I promise you, with with these math, with the regular physics homework, and I know this is confusing to everybody and it's weird, but even if Google Classroom says turned in late, I'm not penalizing anybody for that. The worst thing that happens is, as some of you might have noticed, is I might grade, if yours comes in a little bit late, I might grade it after other people's. But so first of all, it is okay if that comes in late for whatever reason. And I totally understand that we're not really up to it yet in the classroom stuff. So I get that. To answer furthermore though, right, I might even change the date. I have to think about this, but I was thinking right before class. To back up, to remind everybody, what Ashley's talking about is homework 3 technically is still on the docket and is technically due this coming Tuesday, but we're still going over homework 1 in class. That is totally true. Like, we're still going to continue going over homework 1 today. And Ashley's right to expect or predict we're not going to get through homework 2 today, and we may not even finish. We're probably not going to finish homework 1 today. So it's true. I might even change in Google Classroom. I might change the assignment to make it due Thursday. I probably will. In fact, what Ashley's saying, I probably will change the due date of homework 3 to make it Thursday. But even if I forget or don't do that, I still totally understand if it doesn't come in Tuesday. The real deal with these homeworks, with these problem sets is, right, as long as you're turning it in before we're talking about it, you're still very much ahead of the game and on time as far as I'm concerned. But right, so just so Google Classroom doesn't make you feel, I'll probably change that due date. Yes. I mean, so I think the answer to Ashley's question is yes, I'll probably change homework 3 to be due next Thursday instead of Tuesday. But also to say what she's talking about with homework 2 is a bunch of math. Yes. That we need to know for this class. Yes. But we are still going to go over it. I promise you. Like, we're going to be moving faster and faster as as we build a rhythm. We'll be moving through things faster in class. We will go over homework 2. Yeah, we need to know that math for this class, but I'm not really expecting that. That's not like a diagnostic. Homework 2 is not like stuff that you should have solid by this time, and what's wrong with you if you don't. It's not that. Like, it's just we need it. So we got to figure out how well we know it or not, and I got to sort of like teach it to you. I don't expect that you're all perfectly solid with it. It's just laying out like, here's what we do need to know. And so please work your best and your hardest to figure it out as best as you can before we come together. So, but anyway, she's right. Ashley is right that we're still dealing with homework 1 in class here today. Then we still got to go through homework 2. So no matter what, she's definitely right. It's going to be a while before we're even talking about homework 3 in class. No doubt about it. And if we haven't started talking about it, I'm not penalizing any, like, as long as you guys make an attempt at it to turn it in before we're talking about it, you're good. So as long as you're watching so she's right on every count. I mean, and that's what's happening. It's all about, all the due dates and stuff are to show you what the next thing is. And just to be clear to everybody too, what is always the case is I do always expect you guys to be ahead of me. Like, you are supposed to be working on homework 2 or whatever, even before we get to talking in class. By the time we talk about it in class, what I'm trying to do is clarify and explain things that you've already wondered about, that you've already tried hard, so that in a way I'm answering questions. It's like recitation. I don't want to be teaching like totally from scratch anything, just because it's not good for anybody to do. But anyway, so yes, agreed with Ashley's point well taken. And again, if what I'm saying to her makes any sense and she puts in the chat like got it, thanks, then she gets closing a conversation points, blah, blah, blah. Okay. So momentarily, we're going to go back to just continue what we were doing last week, which was in the middle of, okay, cool. All right, thank you. And that was a perfect example. What she just did is a perfect example of closing a conversational path. So she just got points for that, just to be right. Okay, blah, blah. Thank you. All right, cool. And I thank you for thanking me. All right. Right. So in a minute, we're going to go back to going over homework 1. Notice also, it is not a coincidence. Like, notice, we go slower at the beginning and we're going to go faster and faster. You're not the class, say this whole class we have, this whole semester, say there's, I used to know this. I don't know, whatever, say there's 24 classes in the whole semester. That's not right, but I'm just saying arbitrarily. There definitely are not 24 homeworks, right? We spend a while on, so especially the early homeworks, because the early homeworks are meant to lay out a bunch of stuff that we need to churn through. So like homework 1, we're going to go back to in a minute and keep talking about it. And what we're in the middle of right now is problem 4 or question 4 of homework 1. But notice, to do question 4, what I'm ultimately arguing is you got to do energy conservation. Now, yes, there's an equation for that, and we're building it up. And so once you know the equation, right, you can write out the equation, and it's a couple of lines of algebra, and then you've solved question 4. But I'm spending a long time on it because question 4 is designed to be kind of an excuse to let us actually lay out the whole concept of energy conservation and all the mathematical like nuances that we need for this class. In other words, I'm saying a lot about question 4. You might have lost track of where I am. We're deep. We're doing all this integral stuff and everything. Like we got into integrals and work and everything last time. And we have like pages and pages of notes, and we're going to continue them this time. I don't want anybody to think that I think that in order, I'm not trying to say to you guys that in order to answer question 4, you have to give me 15 pages of notes and a whole big notebook on the foundations of energy conservation and work integrals and all of that. It's not that. I'm trying to teach you all that to bring us all up to speed so that then whatever you do write down for question 4 like makes total sense to you and makes total sense to me. In other words, each one of these is kind of an excuse to lay out and unpack a whole topic. You need to have the whole topic in your head. I need to make sure the whole topic's in your head so that then when you, whatever you write down is honest and honestly coming from your head. I'm not expecting, so the fact that I'm spending 6 hours talking about question 4 does not mean that I think that you should give me 6 hours of writing whenever you have a question like question 4. I hope that makes sense. But that's why we go slower at the beginning and faster toward the end. We're trying to lay out everything at the beginning. All right, so in a minute, I'm going to go back to homework 1. I'm going to go back to question 4 and to the underpinnings of energy conservation. Cool. And also, again, in theory, everything I'm saying right now in theory is like old physics, classical mechanics from like the 18th century, from in theory, a prior course in physics or a prior course in calculus, but that's in theory. Like I'm saying it all again now to make it as clear as I can to everybody. So if you didn't get it the first time, don't think, oh God, he's talking about that thing that I was supposed to get last semester, so it's too late, I'm tuning out. Don't think that. But also on the other hand, don't think, oh, he's talking about that thing that I already saw last semester, so I can tune out. No, please. Like nobody gets any, just because you saw it once does not mean you have the whole context of how we need to apply it here. And it never hurts to see anything in a new perspective in a second time and all that. All right, so blah, blah, blah. So, okay, so we're going to go to, so we're going to go back to, we're going back to homework 1, question 4. That's what I'm going back to in a sec. Again, we're leaving early today. Please feel free to remind me at like 1:10. You can give me a heads up that so it's going to be a short class. I apologize. And then I'll see you again on Tuesday. There's one other thing. Oh, and hopefully, one other thing. As far as homework, since Ashley reminded me, this is my belief in terms of who's ahead and who's behind, whatever. We did have this holiday, but it actually was a holiday for my people. Like I was actually celebrating and observing with all my family and stuff like that. So it was actually not total free time. So I'm still a little bit behind. What I'm trying to say is this. I believe at this moment, everybody in this class, I believe that everybody in this class has gotten back anything and everything they've given me. Like all game assignments, I think that have come in have come back. And all of homework 1, anybody who gave me any homework 1, I believe, even if it was like as of 5 minutes ago, I believe they've all come back. I believe very few people got a 20 out of 20. Again, if you got anything less than a 20 out of 20, you have infinite time still, not right now, but like look at what I marked, what I said was imperfect or whatever. And you could just resubmit whenever, not right now, but you can resubmit for the remaining points. Whatever score you got is just an indication of how much more work you have to do to get the full score. Okay, so I believe everybody has gotten draft 1 of homework 1 back with a score. Most scores were good. Most of them were very impressive. They were, but most scores were under a 20. So there's still things people can do if they want. And then also you can just let alone and keep going. Like they're just points. They're not a percentage. But nobody, just to be clear, this is what I'm trying to say, nobody's gotten back homework 2. A lot of you have turned in homework 2. It was due. Thank you very much. I'm totally aware. I think I read the names out last time. I know I have homework 2 from a lot of you. I have not even gotten up to turning that back yet, and we haven't gotten up to talking in class. So it's not personal to you if you haven't gotten it back. But I believe everybody should have gotten everything back besides homework 2. Okay. And again, if I wrote things on your homework 1 that you don't understand, like if I wrote like www somewhere and took off a couple of points, or if I wrote WIQ and took off a point, I did try to give like a quick code like sheet of what those things mean. I mean, in notes in class like 2 weeks ago. Please look back in the video or whatever, but it is there and it's in the notes somewhere. But like in short, WIQ means what is the question? You need to give me the question first before you go on and start answering it, especially when sometimes people do this, especially like in a hard question like question 9. A lot of people would write, like for question 9, they write, I have no idea how to do this. Well, question 9 is very hard for sure. And I could be very generous about like various attempts that people make, even if they don't get the right answer. But you can't say, I have no idea how to do this if you haven't even written down what it is that you're trying to do, that you have no idea what to do. Like step 1 always is write down what the question is. Then step 2 is define the terms in the question. Like there are steps that you can always go through before you decide you have no idea what to do. That's kind of what we're trying. Anyway, whatever. So WIQ means what is the question? WWW means what, where, sorry, WWW means what, why, where, from, which basically means you just suddenly put down an equation that I think was out of nowhere, i.e. from the web. And like, it wasn't justified. I don't know why it applies. I don't know how you understand it or why you understand it. And I don't know what you're doing with it. It basically means you have to show a lot more work and justification. That's what WWW means. WIQ means what is the question. PCA means please circle answer, stuff like, there's other things like that, but they're in the notes from last week. Okay, I'm going to shut up. I know we have a lot more to do. Okay, so we're going to energy conservation. I'm just going to pause for a second so you can write this down. Technically, this is just review or reminding us where we are for continuity. So I'll just let you write this down. But well, what it's saying is, so I'm just reminding you of the picture of the situation, reminding you the question is at x equals 0. In other words, at equilibrium, what's the instantaneous speed or the instantaneous velocity? And remember, that's not the same as average velocity. We're asking how fast is it going at equilibrium. And the thing's been moving in from the initial spot of 15 centimeters. So it wasn't going at all initially, and then it started moving. So presumably it's going, and so it accelerates. It's got more and more speed as it's going in. By the time it gets to the equilibrium position, I presume it's going to have a lot of speed, or at least more than zero. And we want to know how much that speed is. Like, I don't think it's going to stop right when it gets to the equilibrium position. It may start to stop. It might start slowing down, but you can't do that in one instant. It's not a cartoon. So it's going to have built up a lot of speed by the time it gets to the equilibrium position. We're looking for what that speed is that it has at that moment. And just what I wrote in English here is that thus far, as in last week, we established that this question is now going to compel us to think about energy, to think about work and energy conservation, because forces and accelerations are no longer good enough for looking at. Like, we had a whole big discussion about this last week, but remember, the force is not constant. Shorthand for that, F does not equal F naught. The force at any moment does not equal what the force was at the very first moment. So that's a shorthand way of writing force is not constant. Similarly, or by the same reasoning, acceleration is not the same as what it was at the first moment. Acceleration is changing. When the force and the acceleration are changing from place to place, but you want to know the speed at a given place, we said that's where energy comes into play, right? So we started reminding ourselves of how energy works and what energy has to do with work and all that, right? So I started reviewing all that. I started backing up. Like, we wouldn't have to go through all this in our mind every single time if it was all at our fingertips, but presuming that it's not, we backed up. Now I'm going to turn the page. Tell me if I'm turning the page. Let me know if you want to go back on the page, but I'm turning the page. I'm saying what we've established so far, there's this definition of work, we said. And ultimately, if you're taking into account forces that change continuously throughout some displacement, in order to account for that type of thing, we defined, right, like the business, all of that stuff we were saying last week was in principle just to remind ourselves or establish or justify or unpack this definition of work, which is the integral of force with respect to displacement. Like, that's what the definition of work is. It's an integral. Then I try to remind you or use as an example of trying to really explain what the definition of an integral is. I'm not going to do that again right now, but I do think that work is like the most vivid, clear example of what an integral is in like all of physics and math. Remember, it's a continuous sum of products. Now, technically, one of the okay, just a little vocabulary here. And I didn't say this last time. This is actually going to become sort of helpful or important. So I'm not saying that every integral in the world is work, or like work is an example of an integral, right? And it's an integral, it's force being integrated with respect to dx, where x stands for position, right? And dx is some infinitesimal change or difference in position. Now, what's a difference in position or a change in position known as in physics? It's known as a displacement, right? So work very specifically is the integral. It's not just like, it's the integral of force where so force is the dependent variable. I guess that's what I'm trying to say. force is the dependent variable, and the independent variable here is x, or position. In other words, space, right? Dependent variable. Like this is just like with derivatives and stuff. With functions in general, you want to be super explicit all the time. What's your dependent variable? What's your independent variable? What's your output? What's your input? Makes all the difference in the world. Like that's why we're clear about, we try to be very precise about this notation. We don't just take the derivative of blah. We take the derivative of blah with respect to blee, right? Like acceleration isn't just the derivative of velocity. It's the derivative of velocity with respect to time. It is the derivative of velocity when time is treated as the independent variable. If you differentiate velocity with respect to space, you're allowed to do that too. That's a totally legitimate mathematical thing to do, but it wouldn't be called acceleration, right? I'm just saying we have to be clear and explicit all the time about what our variables are. So work is the integral of force when we're integrating force along or with respect to or as a function of various positions that we're changing. So we're integrating force along literally a path. Now, quick side note, you might say, yeah, I don't love integrals, but I thought I mean, aren't we always integrating along a path in math class? Like, aren't you always integrating along the x-axis in math class? Well, in math class, yes, whatever you're integrating along, you call the x-axis. Like if you think of graphs, if you make a graph, yes, you're always adding up like a bunch of rectangles along an x-axis and taking the area under the curve that you formed on the y-axis. But my point is that's math. The x-axis could stand for any variable at all. Like often in physics, like exactly the point. Right, like the x-axis stands for the independent variable, and quite frequently, quite generally in physics, exactly what Sam just said, like quite frequently, if the independent variable is time, and we absolutely integrate with respect to time a lot. So that's good. So what I'm trying to say right here is, let's just be clear here, we're looking at how some force acts along an x-axis that actually does represent a length or a pathway or a displacement in true actual space. I mean, to be totally honest, if this works for any of you, like we could take the integral of f with respect to dt, and that's called impulse. And what that changes is linear momentum. Like it's a totally legitimate thing. It's just another different thing. What we're doing here is walking along some path through space. We're walking along a displacement, like from a position in space to another position in space, and asking how strong the force is acting throughout that displacement. So A, that's what work is. B, I want to say to everybody now as a mathematical thing, whenever we integrate with respect to space like this, when we integrate anything and make the independent variable, the integration variable dx, like we're doing here, that is called from now on in math and physics, it's called a path integral. Like not all integrals are path integrals, but all path integrals are integrals. A path integral is very specifically an integral through space, through one dimension of space, okay? Just as a vocabulary thing that we're going to use later. So work is the path integral of force. Like that's what it is. It's the integral of force with respect to space. It's the path integral of force. Okay. So good point, Sam. Okay, I'm just going on. Okay. I think that was it. Yeah. Okay. And I'm just looking at the time. Okay. Now, what am I going to do with this? I want to do a couple of things with this. Again, I'm kind of going to review some possibly old physics concepts here to just reestablish for the sake of question 4, but also I'm trying to show them in a slightly more sophisticated mathematical light. So please follow along with me, like whether they're old or new to you. Like what I'm saying is this. Sorry. Okay. Now keep. Oh wait, someone's in the chat, or is that? Oh. Oh wait, great question. Oh no, great question. Okay, this is a question in the private chat. Great question. I'm not going to say the person's name because it is a private, but I'm going to sort of. So there's a question in the private chat about. So will a path integral, when we're solving in terms of actually solving problems, which is certainly what I need to get to here, in terms of solving problems, will path integrals be different from regular integrals? I think that's what the question's asking. Will a path integral be different from a regular integral? And no, I don't mean to say that. What I'm trying to say actually is that, I mean, again, great question, but I think the answer is no. I think, oh, okay, cool, great, thank you. I think what I'm trying to say is that a path integral is a subset or a special case, a specific case of a regular integral. So it won't be different. It's just, in some ways, often, once we know about path integrals, in some ways, so often it'll be sort of easier or simpler because once we do one once, then we know it for all time. But no, it's not different from a regular integral. It's just like a special case, a subset of regular integrals. That comes up a lot. I mean, basically in physics, we're generally either integrating with respect to time or we're integrating with respect to space. We're just trying to tell ourselves in advance all the time. We just want to be clear to ourselves before we dive in to know which one it is, because it'll just make a difference in terms of which one to use when. But no, it won't change. Anything you know about how to integrate will still be true with a path integral. But I think that's a great question. Okay, great. Oh, and the person in the private chat just totally closed the loop too. So even though it's private, I hope it's clear to the person in the private chat. Person in private can totally submit all of that for extra points for closing conversation, everything, even though it was private, is fine. Like, especially because apparently I did. Okay, so great. Okay. All right. So I'm going to say. Oh, wait, sorry. I'm going to add one other constraint here. And this is a funny dance that we always do in physics, right? Like, we're inventing methods to deal with more complicated situations, but we always kind of test and we invent methods for more complicated situations, but the way we invent them and test them is by first applying them to the simple situations and then blowing them up. We're always going back and forth between simple situations and complicated situations because of our belief that a complicated situation is just lots of simple situations put together. So we're always just trying to boil down to our ingredients and then put the ingredients together to make the soup, so to speak. So I'm going to say this. The reason that we're doing this whole energy dance, the reason that like we even invented energy idea in the first place or discovered it in the first place is in order to deal with forces that change. But the way we test out our ideas and the way we examine the ideas of energy is always first with little sections of force that don't change. Again, because of this whole idea that if I know what to do with one constant force and I know what to do with another constant force and I know what to do with another constant force, I'm just going to add them all up and then I'll have the changing force thing. So we're going to assume for the moment, let's assume that we have a force that doesn't change and is acting in a totally simple way, like pushing along the same direction as a displacement. In other words, picture, you might want to write this in your notes. I feel like I'm babbling too much, so I'm not going to write this, but you might want to write, like, example of what I'm saying is picture that you're pushing a box that you're pushing a box with a purely horizontal force and the box a purely horizontal and constant force, and the box is being displaced in a purely horizontal way. In other words, picture the simplest situation you can. We're just pushing something through a horizontal displacement, right? And if we do that, we use this definition, then if we assume that it's all horizontal, then those arrows, those vector arrows, we don't have to worry about them because vectors are all about direction. If we assume that all the directions are as straightforward as possible, Okay, so I'm saying that's our definition here. Okay, so notice I start with a triple equal sign. The definition of work is technically integral of force with respect to displacement. Then I'm saying now I'm relaxed. I'm saying if we assume that all the arrows are pointing the same way, then we don't have to worry about the arrows anymore. We don't have to worry about vectors if everything's like a long number line. So I'm going to a double equal sign now, right? And then I'm assuming, and if we're assuming that F is constant, right? If F does not change with respect to dx, then if it's a constant, right, you would take it out of the integral, right? Now, I'm not saying you could do this every single time. I'm saying in this simple case that I'm looking at for the moment, right? So I'm using a integral to cover my general situation, and I'm specifying in this case a constant force. Then, so F is constant, it comes out. So then I would say, in this simple case, we would have the tech. This is where in a lot of like 8th grade textbooks or something like that, where they say, oh, work is force times distance. They're just taking the limiting case of our general definition, right? In general, work is the path integral of force. But sure, if the force is simple enough, then work just ends up being force times displacement, right? Okay, now why am I doing that? Because then right now I'm saying, now again, this is technically a reminder of something you've seen a long time ago, but you might not have, maybe it'll be clearer now or whatever. I'm saying, well, in the case, if in a case of a simple horizontal constant force pushing a box along a table or along a floor, right? Work equals force times displacement, but we know that net force equals ma, like Newton's second law, right? So if we want to know the net work being done on this object, the net work would be, well, I guess I could add a line and say, so net work would equal net force times displacement, right? Therefore, the net work that we do on this block would be ma times x. I'm just substituting in. All this talk is just for me to make a substitution of f equals ma into w equals fx. But now, saying that, I could say, right? If the force is constant, then acceleration is constant, right? So we can use our constant acceleration equations, one of which is this. You may or may not remember it from last, but it is, right? I mean, that's just one example. So I can and why would I even think of that? There's other equations for A2, but if remember our whole thrust here, our whole context here is we're in a situation where we're trying to predict how much speed something gains from one place to another. We're looking for a speed place relation. That's really what we're trying to use work and energy to get for us. We're trying to figure out how to relate speed to place, right? So I'm using an equation that relates those things, speed and place, to acceleration. So I'm going to substitute in now, and I'm looking at the time. Okay, we got a little time. All right, so I substitute in. Tell me if you want me to go back. right? So now, so I'm just substituting in. Uh, um, oh, and I'm sorry, and also cancel out the x's, sorry. Like the x's cancel, there's an x on the top and there's an x on the bottom, right? So x divided by x is 1, right? So they cancel. So we have now, many of you have seen this in one form or another, or now that I'm writing, you may not have known where this was going, or maybe you did, but you might recognize these 1f mv squareds that are suddenly just popped into my life right here. I'm just trying to show you all where they came from in the first place, like what we just showed, okay, what in this, at least in this simple example, right? What we're saying, I'll write again the next page, but this is, so in theory, this is old physics, right? In theory, but I don't care about but in this, but I want to remind you of it, if nothing else, and I don't want anything to just go assumed or unproven. What this shows right here is, as long as we define work, as long as we just define work to be the path integral of force, right? Which is like saying we define acceleration to be the first time derivative of velocity. Like we're just doing mathematical operations on space-time measurements that we already have and defining new space-time measurements. So if we integrate force along some path, we call it work. One of the reasons that's useful to do, why we even care to do that, to look at that, is that it seems that, at least in simple cases, and it turns out in all cases, it seems that then with that definition of work ends up being equal to, well, or let me write this on the next page, equal to a change in some very important combination of measurements of a system. Let me write this on the next page and tell you what I mean. Okay, well, hopefully you recognize 1f mv squared as something here. What I'm trying to show you though is this is the first appearance of 1f mv squared. If you've ever memorized or told yourself or learned in any class at all, oh, 1f mv squared equals kinetic energy, there's a reason for that. Here's the reason, okay? The reason we ever started paying attention to 1f mv squared is that evidently, and I'm watching the time, okay, evidently, if you do a little bit of work, like a simple amount of work onto a system, then, well, let me back up for a second. Say you take some system, you take like that block that you pushed along the table, okay? And you measure its speed at this moment. Okay, and then you come along and you do a little bit of work on it, like you push it through a displacement, and then you measure its speed again. Well, the amount that its speed changed by is not exactly the same as the amount of work you did on it. Like work is not that directly useful a concept. Or let me be more specific. If you exert a force through displacement on the object, if you push it with this number of newtons, if you push it with this number of newtons and you push it through 3 meters, we said last time that's called doing 15 joules of work, right? Like I just forgot the numbers I just said, but like if you do 5 newtons of force through 3 meters of displacement, a newton times a meter is called a joule of work, right? So say you do 15 joules of work on a system and you measure the system's speed before and after. No one is saying that life is so simple. Life is not so simple. Nobody's saying, oh, if you do 15 joules of work on a system, the system will go faster by 15 joules of speed. No, we're not saying that because speed isn't even measured in joules. Like that wouldn't even make sense. But we're saying something darn close, something darn close and exactly as useful once you understand it. What we're saying is if you take a system and you measure its speed and you measure its mass, and weirdly, you take its speed and square it, and you take the mass and you have it, and you multiply the two together. Like weird thing to do. Like, I don't even know why I would ever do that. I'll tell you why. Like I wouldn't have thought of it, but apparently this is telling me to do that. If I take a system and I measure how big it is, how massive it is, and I measure how fast it's going, and then I combine those two measurements in a funny way. Like I square the speed and I multiply it by the mass and then divide by 2. Like, and then I write that number down on a piece of paper. Like, again, very weird thing to do. I would never just do this just because I felt like it. And I would never know that it should be significant to do this, except that apparently I just stumbled on a proof that says so. If I take a system and I write down half of its mass multiplied by the square of its speed, so I take that combination of, very good. I was just getting to that in a second. Very good, Stephanie. Yes. Like, and yes. So if I take its speed and square it, and multiply that by half of its mass. First of all, what Stephanie's saying that's very good, like on really, is that actually then you'll have something that's measured in joules. That's right. And in fact, let me write this. Yeah, like that's really good. Well, okay, I'm gonna write it down in a second. But yes, it's like, because if you multiply kilograms times meters squared divided by seconds squared, right? Because we're squaring the speed. And I will write this down in a second, but she's absolutely right. That's a great insight. And it totally shows that she is following what I'm saying and maybe getting bored at this point. Kilogram, like remember a joule is like a newton times a meter. It's a newton is a kilogram meter per second squared, like F equals ma, like it's mass times acceleration. So a newton is a kilogram times meter per second squared. A newton times a meter is a kilogram times a meter per second squared times a meter. In other words, a newton times a meter is a kilogram times meter squared over second squared. That's what a joule is. So that's really good. So yeah, so that's a hint right there that something is going on with this combination of factors. If you take something's mass and you multiply it by the square of its speed, and then for reasons that we would have never guessed, but just come out from the math, if you take the whole thing divided by 2 and you write that number down, think of that as just like a defining property of the system. It's like its mass square speed, we could call it whatever. You write that down. And then you do a certain number of joules of work on this system. What we're like, if you do positive work on the system and then see how fast it's going now, measure those numbers again, write them all down, then compare the new value for that half mass square speed number. What we're saying here in this equation is the change, the difference between 1/2 mv squared now versus what 1/2 mv squared was a couple of moments ago before we did the work. The gain in the 1/2 mv squared is precisely the number of joules of work that you did on the system. That's what we just proved. It's like a sneaky sleight of hand, like weird algebra, like now you see it. But it's what we're doing here is we're saying the triple equal sign of work is path integral of force. Like what work is force through displacement. Why do we care? Because what work evidently does, if you just crank the algebra, what the impact of work is on a system is that it changes its 1/2 mv squared. 1/2 mv squared is the combination of measurements that apparently equals joules and apparently gets exactly affected by every joule of work you do. So we're going to give a name to that. So sorry. So first of all, let me write down the thing that Stephanie just said. That's really good. And by the way, 1/2 has no units at all. So the 1/2 doesn't change the units argument. Let me just see what's in the chat. I think. And thank you very much. Awesome. Yes. So thank you, Stephanie. Awesome. And thank you, Nikaya. Totally true. Thank you. Right. So I'm going to try to start wrapping this up now, or at least get us can I get us an answer for question 4? Okay. Yeah, I'm going to try to start wrapping this up now. I totally appreciate it, Nikaya. Okay. So what I'm saying right now is that statement that we just did on the back page shows us that it's worth paying attention to 1F mv squared. That literally was what it's saying, is pay attention to 1F mv squared from now on, because that's the combination of measurements that changes or is transferred according as a function of work. So we give it a name. So from here on in, we call 1F mv squared. We could have called it anything, but we're going to call it kinetic energy, right? Like, okay, again, I'm not saying that we just proved that some new concept is related to some old concept. I'm saying this is where the concept comes from. From now on, kinetic energy is 1F, is the kinetic energy of a system is the 1F mv squared of a system, because that's just a package of measurements that seems to change perfectly and precisely, predictably, according to how much work is done on the system. So it seems to be the consequence of doing work on a system. And now on, in other words, we say, and again, I know some of you, especially if you're from other schools, whatever, have seen this before, or you've seen it in high school, but I'm just trying to put it in this perspective now. So forgive, please. So I'm saying, the time, she's right. Okay. Let me just think for a second. I know this still doesn't get you an answer to question 4. And that's just the way it is. Let me just think for a second. Okay, yeah, let me just summarize what this page says. And I know it still doesn't get you an answer to question 4. Hopefully this clarifies some concepts for us that will help us go on in physics. And again, I'm aware, I know where we are in the homework, so it's on me, not you. But I know we still haven't gotten an answer to question 4. I mean, I do think the answer is 3.87 meters per second is the answer to question 4. And by the way, if you're tracking, I think the answer to question 5, if you care or whatever, because a lot of you got question 4 right. Well, okay, let me stop that for a second. I'm going to finish. I'm not going to start any new pages. I mean, Nikaya's right. Again, thank you for the time reminder. I'm just going to read aloud or summarize this. I'm going to say something quick about the homework, and then we'll go for today. And my apologies. And I will make up the instruction time somehow, maybe even in a YouTube video or something. But why we just did all this work today is to put in perspective that what work is from now on, like what it's defined to be, is the path integral of force. Like that's what work is. Now, why we can't, and we invented it ultimately to take into account situations where force changes. Like that's why we integrate. But by looking at a little situation where the force doesn't change, by looking at a little situation, we found that what work does, and this is what I'm trying to say here, what work does is it changes the 1F mv squared of a system. Let me be more specific. And so then I say 2 things about that. One, I'm saying we found it out for some little bit of work over a little displacement, but the whole principle of integration, the whole concept that we were sort of stressing last time of superposition and stuff, is that the whole is equal to the sum of its parts. So if for any little bit of work that we ever do, we find that what work is doing is changing the 1F mv squared of a system, then, well, any big amount of work is just the sum of all of its little works, right? So even if it's hard to calculate, or even if we don't have methods yet for perfectly calculating, we could still believe that any result we got for a part must, as long as it's true for all parts, must be true for the whole. So what we conclude today is that what work is the integral of force with respect to displacement. What work, or at least net work, does to a system is it changes what from here on in we're going to call the kinetic energy of a system. And I say it changes, like, to be very specific now, to take into account signs, positive and negative signs. If you do positive work on a system, you increase its kinetic energy, right? If you do negative work on a system, you decrease its kinetic energy. Like if you push something forward, you make it go faster and faster. But by Newton's third law, while you're pushing it forward, it must be pushing back on you, right? And you're getting slower and slower. So when we do positive work, we increase kinetic energy. When we do negative work, we decrease kinetic energy. So the best way to put that in a way is work, and the best way to picture this from now on in, work is the transfer of kinetic energy. Like, and please write this down some way if it's not already clear. Like, work is the transaction, kinetic energy is the commodity, right? To do work onto something is to pass kinetic energy from the worker to the workee, like quite literally, right? Kinetic energy is like this bundle that we have, so like our half mass times square speed, and we pass it around, or portions of it around, by doing work. Work is the transfer of kinetic energy. In fact, this is the last thing I'm going to ask you to write this somehow in your notes, like even on that page or whatever. Work is the transfer of kinetic energy, okay? Kinetic energy is the ability to do work. It sounds like a circle. Please write that though. Like, even if you've heard it before, work is the transfer of kinetic energy. Kinetic energy is the ability to do work. May sound like a circle, but it's just like money, right? Money is the ability to spend money and buy things. right? In a transaction, I pass some money to you. Whatever I lose, you get. Money is the thing that I have some of, and then you have some of. The transaction is the act of me passing some to you. Work is the transaction. Energy is the ability to perform that transaction. It's also the net result of that transaction. It is a circle, just like money is. Why do I want more money? So that I can spend it, right? Okay, that's the point of all that. And the last thing on the homework, just for what it's worth, the answer to question 4, and of course, I'm going to get to this on Tuesday, but the answer to question 4 is 3.87. However, a lot of you just got that by writing some equation down that had omega in it. Like you wrote something like omega equals, or like V equals A omega or something like, I know that equation. I know it's right, but I don't think you knew. I mean, you got to show me, like, we didn't say anything about omega in any of this. You can't just pull out an omega and start doing things, even if it says on the web that that's true, right? The way to get question 4 right is to use kinetic energy and work, or ultimately, when I introduce next time, potential energy. But like omegas don't have anything to do with what we're talking about yet. If you want to introduce one, you got to prove why. But in any case, the answer to question 4, the correct answer is 3.87, however you get it. But the answer to question 5, just so you know, the answer to question 5 is 0.095 meters. It's a lot of people got question 4 right, but then because they really didn't know why they did what they did, and they just like copied an equation, then they copied that same equation for question 5, and it doesn't work the same way for question 5. So I want you to, so just so you know, if you're like checking things or following along, the answer to question 4 is 3.87 meters per second. The answer to question 5 is 0.095 meters. We will get to that on Tuesday. I have to catch up with you. You have no new work. I promise. I'm going to. Thank you so much for being so patient. I'm going to end now, which is 10 minutes early, 1:20. But totally appreciate your patience, but goodbye. Thank you. Have a great weekend. Yes.
Have a good weekend, Professor.
Thank you. Thank you so much. Bye. Thank you. Have a great weekend. Yes. Great. Great. Thank you. Okay.